talk today. We're happy to have Kaave Hosseini tell us about sign rank versus margin.
Very much. So this is a joint, it's about 3 different works with each one, the authors being a subset of the people here. 3 different subsets. So it's Ahmed, Shahar, Ben, who's here, and Morgan, and also Xiaoming, who was an undergrad at McGill. Okay, so what is this talk about? It's about some different notions of rank that turn out to be important in many different areas. Let's first define these different notions of rank, and then we'll see the motivation behind them. So let's say, what is real rank of a matrix? Well, one way to view the rank of a matrix is let's say you have a +1 -1 matrix, it's n by n. You want to look at the rank is the smallest dimension d, where you can find vectors x1 up to xn, 1 for each row in Rd, and y1 up to im, 1 for each column in Rd, so that the inner product of xi, yj is whatever is the ij entry of the matrix, right? So in terms of like factorization, the x's correspond to the rows of the first tall matrix that you have in the factorization, and y correspond to the columns of the tall matrix, the fat matrix, right? So let's say you're bored with this definition and you just want to change it somehow. So there are 2 things to play with, right? One is this condition that vectors live in Rd, and one is this condition that things are equal. So let's first try to alter the green condition. So how can one change that to make it more relaxed? Well, you can just say, well, I just want the product of these to be some number between 1 up to whatever constant, let's say 10 or something. Okay. So this is supposed to be tilde, but I don't know why it's not fully showing here. So maybe I'll improve later. But so here it was, this product has been 1 and 1, right? So I'm just changing this side to be some alpha. So this is called approximate rank. Another, even you can further relax it to say, well, alpha is infinity. And this is called now sign rank. I could have put infinity here. And so you just want to preserve the sign. So here I could have put 0. It wouldn't make anything because I could just scale the vectors, right? And let's say sign of 0 is +1. So if this was 0, I consider that to be a +1 in the matrix. Okay, so that's 3 different definitions. We can now try to relax in the other dimension, relax the red requirement. So what does that correspond to? Well, a natural condition, instead of looking at the dimension of the vectors, is to say the vectors can live in whatever dimension, I don't care. So it's n plus m vectors. So let's say this is our n plus m. But I require that the length of these vectors is short. So I want to find the smallest L where I can find these vectors, where for every ij, the product of L2 norm of these vectors is at most L.
Why is it naturally constrained the product of the norms rather than like individually the norms?
Good, it doesn't make a difference, right? Because if it was individually, you could just go back and forth between the maximum of all xi's and xj's and the product. You'll just lose a squared.
And just losing
Because I can just scale one side, it doesn't matter, right? Because I just, yeah.
But losing the square doesn't bother you? You're okay with it?
Here, everything is about Pauli relations, so it doesn't really make any difference. Actually, do I even lose any square? Yeah. Yes.
So in the sign rank, if aij is 0, what happens?
So it's, let's say you
It's
take the
+1
definition to be 0 here, and if the 0, the sign of 0 is plus, let's say. Let's say 0 times 1 equals 1. Right? It doesn't make, and let's say you're really uncomfortable with that. Well, you want to never get 0 because that might be weird. You can always bump the dimension by 1 extra dimension to say you can never get 0. Right? And just make sure none of these inner products are 0 if you have 1 extra dimension. Just put some like infinitesimal in the extra dimension for everybody.
Right. But the aij can be 0, right?
No, this is a +1 minus.
Oh, okay, there's a plus on minus. You're only defining.
Yeah,
But
it's a
actually,
sign
it
matrix.
makes
It's,
sense.
it's only about sign patterns. It's not
The definitions do make sense for arbitrary.
for arbitrary. Well, I mean, you can just put 0. It only makes sense for either this type of matrix or +1 0 minus 1 matrix, and then you want to treat 0 especially and call. And in the 0, you really want this to be 0, right? That would be a different definition of sign rank, which I'm not sure if it's equivalent.
So this version of gamma 2 is efficiently computable?
Right. So the benefit of this gamma 2 and the relaxations is it's in computer, right? Because you can write some semi-definite program, and this would be the optimum value, right? Rank is easily computable. It's a lucky thing, but these two things are hard to compute. And in fact, it's a result of Amai, might be here, and Koparty, who showed that this is, even to decide if this is 3 or not, it's NP hard. And in fact, it's even harder than NP hard. But existential theory of the reals hard. But here, the good thing about these type of norms is that it's computable easily. Okay, so is the definition of gamma 2 norm clear? Okay, so let's now try to, in this direction, make it relaxed. So gamma 2 tilde, again with some approximation factor alpha, is I just now require this to be true instead of exact equality. And I can further again relax it to say that gamma 2 infinity is I just want to every inner product to be, every product here to be at least 1. Right. So the template, the meta question in this talk that I'll be talking about has the following template. I'm picking one of these norms, one of these parameters, and I'm saying if that parameter is small, how large can the other parameter be? Okay. So there are 6 parameters, and this question there, you get 6 times 5, 30 questions. Many of them are trivial, so we'll be talking about non-trivial, some of the non-trivial ones, and even still not all of them are resolved. But turns out that this question has different interpretations in many different areas, and it relates to a lot of different math. Okay, so let's just see an example first. So this is the identity matrix, correspond to the equality function. So the rank is n. The approximate rank of this, does anybody has a guess? Who hasn't seen it? So let's say by approximate rank, let's say now from now on, I have my alpha parameter is some like 10 or whatever, it doesn't matter. So it's an absolute constant. So this is a result of ln that shows the approximate rank of identity is log n. Okay. And now what about sign rank? What do you guess for the sign rank?
Do you have any intuition for why?
Good, I'll give you an intuition for a second. But without intuition, any wild guesses?
Order 1.
Wow, okay, that's a good intuition. Okay, so yeah, what would be some intuition for sign rank? So how would you think about the sign rank of a matrix? Let's say again, you have this plus minus patterns. So I want to pick for each row, pick an x, like so x correspond to a particular row, y correspond to a particular column. And I want, if it's positive, if it's plus, I want this to be positive, right? In other words, if you think of this y as the normal vector to this hyperplane, then I just want this x to be on the positive side of this half space that's defined by this hyperplane, right? So basically, for each column, I can just say I have these half spaces, and I'm just checking inclusion. Am I on this side of the half space or on the other side? And these half spaces are homogeneous, but let's just say I relax the requirement to be just arbitrary affine half spaces. Because if I get an arrangement like this, then I can add 1 extra dimension to make everybody be homogeneous again. So now you can think of this as just some incidence matrix of this inclusion problem, right? You have, for each row, you have a point in RD, and for each column you have a half space, and you put a plus if the point is in the half space, or if it's put minus if it's outside of the half space. And again, let's say I'm not on the half space exactly, or if I'm on it, let's just say put that a plus, right? So this is a closed set. Okay, so with this intuition, can you have an arrangement of point hyperplanes or half spaces for equality function, for identity? So here's a simple arrangement. Just put for rows, just put them like this. Okay, now the half spaces, each point has a unique half space that only there I'm plus on the diagonal, right? And everyone else must be minus. So I mean, this is the separator. So this is the half space for this point that's only separates out this point, right? So for each point, I get this corresponding half space for the column, the same column, right? Okay. So this is in 2 dimensions. But again, these are not homogeneous. In the definition, I required homogeneity. So I can just increase the 1 extra dimension to make everybody pass through 0. So the sign rank is 3. Okay, so what is the gamma 2 norm of identity? I'm not going to waste too much time, so I'll just say it immediately. It's 1. So gamma 2 norm is 1, and everybody else is smaller, so it's also 1. And also you have to be at least 1, right?
Do things change if I require symmetry? Like if I require that x and y, like xi equals 1, 1?
Good. So that's a very different question, right? This is generally a bipartite type of question. And if I require to pick the same vector for the row and the same column, it's a different question. Like in that case, like all minus would be hard, right? Because that corresponds to just picking a bunch of points. Everybody is or less than orthogonal, has negative correlation with each other, right? So this is here you want to really capture complexity in a way that these basic objects like all 1 or this sort of thing is easy, right? So this is very different than the symmetric question. Okay, so instead of juggling with 6 parameters from now on, I'll only focus until foreseeable future on these 2, sign rank and gamma to infinity. But Glenn will talk about the other parameters.
So isn't the intuition here that in communication, like this, the deterministic randomized and
we'll get into that too, right, the connection. But for now, there is no communication complexity. Okay, so let me just motivate sign rank a little bit. So sign rank turns out to be a crucial parameter in learning theory. So in learning theory, it's called dimension complexity, and it's used to prove lower bounds on learning problems and also obtain algorithms. In fact, as an example, the best known learning algorithm for DNF due to Clive and Servideo is by obtaining a strong upper bound on sign rank of DNFs. Okay, so I won't get into details of any of these. I'm just casually throwing some keywords about connections of sign rank to different areas. So that's in learning theory. In communication complexity, it's a crucial concept. Why? Because it turns out that log of sign rank is exactly this concept, unbounded error communication complexity of A. So this is a model where you look at randomized communication complexity, but you just want to beat the pure random guess, which has error half. You just want to have error at strictly less than half. I'm not going to define communication complexity because if you don't know it, it doesn't matter for the motivation, and everything will be fine without the story of communication complexity. But if you know it, it's just extra motivation. So this is a plus minus 1 here, but it doesn't matter. So this is a result of Paturi-Salmon, and yeah, so basically this connection makes it highly relevant in communication complexity, right? Because this model is important and people want to understand its relation to different models of communication. So that's in communication complexity. In circle lower bound, it's also important because you can use it to prove lower bounds on some certain types of circuits. For example, for this ridiculously simple type of circuits, thresholds of majority, whatever that means, it's like a 2-layered circuit. Proving lower bounds on sign rank implies proving lower bounds on these type of circuits. So this is one application in circuit complexity. Also, it's a highly relevant parameter in semi-algebraic community. So semi-algebraic graphs are basically, sign rank becomes one of the most important parameters. In fact, one of the very important open question in the area is that semi-algebraic graphs of bounded complexity are precisely those that have bounded sign rank. So what was sign rank? It was all these arrangements of incidence of half spaces and points. You can generalize that, right? You can just say, well, instead of half spaces, I can, for each column, I could have some like semi-algebraic set, which is like an intersection of a bunch of polynomial inequalities, and look at the incidence of matrix of that, right? And an important question is, does this, if this is bounded complexity, like all the degrees and the dimensions of the polynomials are bounded, can you say that it's actually, you can just change everybody to be a half space by a slight bump in the dimension? So it's an important open question. Okay, now let's move on to gamma to infinity norm. So this is called margin complexity in machine learning. It's an extremely important parameter in learning theory. Why? Because in many learning problems, when you try to solve it, you could think of it as a plus minus matrix. And sign rank, fine, it gives a good upper bound for learning, but sometimes sign rank could be really large, could be just as big as n, or sometimes n is infinity. So it's just infinite dimension. It doesn't make sense. Like you have all this cursive dimensionality stuff. So if dimension is high, the learning task becomes very difficult. However, if I guarantee you that this gamma to infinity of your concept class or the matrix you define is bounded, then there is this simple algorithm called support vector machines that just, its sample complexity is only squared over the gamma to infinity norm, regardless of how, if it's even infinite dimensional, it doesn't matter, right? So a good sub part of learning theory is about obtaining good bounds for gamma to infinity norms of different problems. So that's machine learning and communication complexity. It's highly relevant because it turns out that gamma to infinity is just basically equivalent to this notion called discrepancy, like 1 divided by discrepancy. So discrepancy is a number between 0 and 1. And so this proof uses Grothendieck inequality basically, and some minimax duality. So because of this connection, it's highly relevant in communication complexity. In fact, it turns out that this log of this gamma to infinity norm, or log of this, is a lower bound on randomized communication complexity. In fact, one of the strongest lower bounds we know. And here also you can put gamma to infinity itself. So in the constant regime, it becomes an equivalent notion with randomized communication. Okay. So this discrepancy is not the same thing as combinatorial discrepancy. In like combinatorics, people, when they look at the matrix, they put uniform distribution on the matrix, and they want to say every set is regular. So you want your matrix to be epsilon regular in the Zemrady sense, right? But here, I'm looking at just finding one distribution that is small. So I want to find a distribution on the entries of the matrix. And under that distribution, I have a low correlation with every rectangle. Like every rectangle becomes like balanced, or almost balanced. Anyway, I won't describe discrepancy because it's just, we're going to work with gamma to infinity norm, right? Okay, so now the first question that I'll be talking about is the following. It's a natural question. If sign rank is very small, is it possible, like how large can gamma to infinity be? Can you obtain some good upper bounds on gamma to infinity if the sign rank is small or not? So there was a lot of previous work on this question. And the best known separation was a matrix that has sign rank log of n. So again, it's a number between 1 up to n. And its gamma to infinity is at least poly n. Okay. On the other hand, also one can show that if the sign rank is 2, then this can be only polylog, cannot be bigger than polylog. Okay, so, but on the other hand, there's also some positive evidence that might say this might be the best separation that could happen, right? Because why? Because gamma 2 norm, like not the approximate version, just gamma 2, exact gamma 2 norm for bounded entry matrices is at most square root of rank. So this also the same thing for approximate gamma 2 norm. And this is a non-trivial fact. Basically, this follows from John's theorem from convex geometry. So given that this is true for gamma 2 and approximate gamma 2, one might think that maybe something similar can be done if you look at the infinity version. So gamma 2 infinity cannot be maybe too larger if sign rank is constant, let's say. But we showed a few years ago that this is not the case. So basically we showed that sign rank 2 cannot be too big, gamma 2, but there is a matrix of sign rank only 3 whose gamma 2 norm is essentially bigger, best possible, right? It's poly-n. And the matrix is, so I won't describe the proof, but I'll just say what the construction is. It's a natural construction. I'm basically just looking at integer inner product. So I'm looking at numbers. So each row corresponds to 3 vectors, 3 numbers. All of these are between minus n and n. And same for each column. And for the corresponding entry in the matrix, I'm putting plus if the inner product is non-negative, and put minus if it's negative. Okay, so I guess the size of the matrix is roughly n cubed instead of, but it's poly n, so it doesn't matter. So the result was, yeah, basically gamma to infinity norm of this is at least poly n. Okay. And I won't describe the proof, but the proof was a lot of technical Fourier analysis over ZP, basically. So we work with this notion of discrepancy instead of gamma to infinity. And the point is that you want to carefully choose a smart distribution under which every rectangle is roughly balanced. Okay, so you have to first find a good distribution and then prove that the distribution has some nice, regularity condition. Okay, so now let me switch to the other direction of the question. So I won't describe proofs, and only I will describe a detail of one cute one-line proof for this question. But other than that, I will skip over the details of other proofs. So, okay, so what's the second question? You can just flip the question right now. Now I'm asking, if gamma to infinity is small, how large can sign rank be? Okay, so anybody has intuition for this? So why one might hope the sign rank shouldn't be too big is because of dimensionality reduction, right? So there is this result of Lineal, Mendelssohn, Scheffman, Schrademan, and Arriaga, Vempala. We show that sign rank is always upper bounded by log of the size of the matrix times poly of the gamma to infinity. So any ideas why this might be true? So there you apply this thing called Johnsson-Lindenstrauss lemma, right? Which tells you can, if you have this arrangement of points, you can always project them down to a log n dimensional space where you don't change the inner product by more than some epsilon. So epsilon, the epsilon parameter I'll be working with here is 1 divided by gamma to infinity. And the guarantee of Johnsson-Lindenstrauss is that this is going to be the dimension. So you just apply that, and that brings you the dimension to log n. And so the question that was asked by Lineal, right, in this work, right, they asked whether this log n term is necessary, right? Because maybe here, because I have this extra condition of gamma 2 norm is constant, or like it's big, it's small, maybe I can do something smarter than Johnsson-Lindenstrauss. Is it possible to just get if this log n dependency over from the dependency? Because Johnsson-Lindenstrauss is about every possible collection of points. Here, you look at these 2 sets of points that every inner pairwise inner product of somebody from here and somebody from here if you normalize the points, they're at least something. Right? You have a lower bound on the normalizing the product. So this is in its entirety, it's still open, the question, but in this work with Hamed and Xiangmeng, we showed that this log n term is actually necessary if you just allow partial matrices. I will describe that in a second. We basically construct a matrix that this is tight. So what is, but before getting to that, okay, so let me just tell you the equivalent story in communication complexity. And if you don't know communication complexity, it doesn't matter, you just ignore this slide. So what is Newman lemma? It's this famous result in communication complexity that says, so now to make things meaningful, I'm looking at my matrix to be 2 to the n by 2 to the n. Newman's lemma says that bounded error public randomness communication complexity can upper bound private randomness communication complexity at this overhead of log n, right? And this immediately implies that this notion that I described before, unbounded error communication complexity in this private model is at most public plus this additive term log n. It's known that this is tight, just again because of Alon's example, identity, equality, right? Because this one is constant there, but the approximate rank implies that this is at least log n. So a natural question to ask is, what about this weaker deduction? Is this tight? What about the relationship between this unbounded error private model compared to a public bounded? Okay, so potentially this could have been just an additive term. Okay. So yeah, this is the question. You want to say if this additive log n term is necessary, and equivalent to what I said before, or we basically add, we say that this log n term is necessary. Okay, so now I'll just tell you what's the construction and say something about the proof. So the construction is not a total matrix, it's a partial matrix. So what do I mean by a partial matrix? It's a +1, -1 matrix, but some of the entries are stars. So it's a +-1 star matrix. Now, what are the definitions of sign rank and gamma 2 norm and all that? It's the exact same as before, except when I check the conditions for the stars, I just don't require those. Don't have the requirement. So I don't have the requirement in the length of the vectors, or if the sign of the inner product is the same as what's here, or whatever, because this is star, right? Just ignore those stars. So everything is well defined still. Okay, so this now what we show is that pick an arbitrary epsilon. So gamma 2 is its minimum is again 1. I'm saying you can even get arbitrarily close to 1. There is a matrix that's its sign rank is basically what's just guaranteed by the Johnsson-Lindenstrauss. So its sign rank is at least epsilon times n. And this is also tight. It's epsilon and it also is an upper bound. So up till this log factor, you're tight. Jordan seems.
I'm just confused by the. Okay, so what it means for these quantities for the partial matrix means you minimize over pairs of vectors type of place that satisfy just these constraints, not all n squared constraints, but just
Exactly.
So why couldn't you take whatever vectors in R infinity, realize the margin?
That's what we do, right? Well, this is about, first of all, the way I wrote it, it's n, it's not infinity, and the dependency question is about dependency on the size of the matrix. But you're looking at infinite version of it. I'll get to that in a second.
Okay.
Basically, to reduce the problem to this infinite version.
Okay.
Yeah, there was another question. Okay. Okay, so what is the construction one can look at? The one that Jordan described, but that was the infinite version. So let's first talk about the finite version of that. So what's the construction? It's this gap inner product. So I'm looking at all vectors in this cube that are normalized to have norm 1 exactly. And I define this matrix just by if the inner product is at least 1 minus epsilon. Think of epsilon to be some small constant, let's say a quarter or something. And if it's less than minus of that, I put minus. And if it's between, I put star. Okay. So the claim is that the sign rank of this is epsilon n roughly. Okay. So how do we prove this? We look at this continuous version. So what do I look at? I look at all units points on this sphere and define this matrix, this infinite by Sn minus 1 by Sn minus 1 matrix, where I, again, if exactly the same thing, right? So what do I claim about this? The claim is that, before the claim, this is also a highly relevant concept, again, in machine learning. People call it half spaces with margin, and it's so it's the properties of this class is very important. But the claim that we have is that no matter how epsilon is small, as long as it's not 0, and for any n, so for any n and any epsilon, the sign rank is full. So this is naturally n-dimensional, and I'm saying you cannot even decrease the dimension by anything. Okay. So potentially, I mean, if epsilon, maybe depending on n, could get really close to 0, one might hope to do something smart and reduce the dimension. But you'll see that it's not true. So I'll give you the proof of this. A little bit of the proof, not all of it. Okay. And so basically, if this, after resolving this as the main lemma, then we get the gap inner product version as well. Okay, so what is the proof of this main lemma? It's basically just a one-line application of Borsuk Ulam theorem. So Borsuk Ulam theorem has 58 equivalent formulations, but the one we're working with is the following. So what does it say? It says if you have a continuous map from sphere to one lower dimension, and there's always this antipodal pair. So there's always a point on the sphere and it's antipodal, there's a reflection, so that they're both mapped to the same thing. Okay, so we're going to use this. How can we use this to prove the bound? So this was the claim. So the matrix, again, the rows and the columns of the matrix corresponds to points here on the sphere, right? And let's say somebody claims that the dimension of this is less than n, the sign rank. So there must be a smart choice of mapping the rows using some map f to one lower dimension and map the y's using some other map g to the same lower dimension so that it preserves the sign of the inner products. Okay, so if two things here were positively correlated, in the maps, they have to be positively correlated. So why is this implying what we want? So let's say for a second that, suppose that the maps are continuous. So in the definition of sign rank, there's no need for the maps to be continuous. I mean, it could be any crazy maps, pathological map that one could find possibly. But here, let's just say it's continuous, so I can just, without worry, apply Borsuk Ulam. So what do I do? So let's even just say only f is continuous. It doesn't matter. So let's say f is a continuous map. Therefore, there must be this antipodal pair. And let's say, oh, this is 1 minus epsilon. So let's say this was your threshold. So pick a pair, x. So x is determined by Borsuk Ulam. So this is given to you. Just pick an arbitrary y that's really close to x. So the inner product is so big that it has to be positive in the matrix. And Borsuk Ulam says after you map the minus x is also mapped to the same thing, but inner product of minus x with y has to have is negative, right? In the matrix, it has to be negative, right? So on one hand, I know that this is true because the maps are good. On the other hand, I know that also because of this and because of Borsuk Ulam, the f of minus x is the same as f of x. So it must be the same thing as this one. But this was positive. Although this, I should have chosen this to be negative, right? Because it's the corresponding thing is negative. Oh, sorry, this should be a minus x here. Okay. But then this just means you're violating the sign pattern between minus x and that's y, right? So this is working in the case that the maps are continuous. If the maps are not continuous, you just have to continuize them carefully. So if the maps are not continuous, I look at some continuation of them that at what cost? Well, I might mess up some of the inner product signs. It's fine, but I'm just saying I might just work with another threshold that's slightly bigger than gamma. After the then I'll get the continuous map with some gamma prime that's satisfying all the conditions. Okay, so that's it. I won't describe the gap Hamming version of this, but you basically just reduce this problem to the gap Hamming. So in a way that if gap Hamming had extremely small sign rank, or sorry, gap inner product, the discrete version, then it would imply that this also will have sign rank less than n. Yeah.
Say a little more about how you find the continuous version.
So the continuous, okay. So you just have the map f and g, and this gamma parameter, which is really big, possibly, is given to you. So based on this gamma, you pick some really small epsilon net, where the inner products are much. Sorry.
Is it a different marker? That's really not visible.
So pick some epsilon net of this sphere, and only look at the values of your f and g on those epsilon net points, and based on that, define a continuous map on the entire sphere, right? And then that messes up some of these inner product because things, if like close to the boundary, you might change the sign, right? But it's fine. You can just say if the epsilon net is really tiny, right? It's you can put another condition, right? You can just there are numbers between gamma and 1. Okay, so this is it for this question. So if there are no questions, I'm going to switch gears again to go to another question. So good. So I mean, what kind of total functions you might want to work with? One natural thing is to just fill up all the stars with 1, let's say, right? Naturally, I mean, the same thing. The continuous version still has full sign rank, right? But once you try to do the same for the discrete version of it, what do you get? So the discrete version would correspond to the following. So I have the vectors that are all, like, say, normalized. These are all these x and y's, and I put some threshold here. If everybody is bigger than that threshold, I put a plus, and if everybody is less than that threshold, I put minus. So this is now total, right? And you can say, well, if I put the threshold to be really close to 1, so what, let's say you put the threshold, this is a number between 1 and, let's say I don't even normalize this for a second. So the inner product is between n and 0. And let's say if I put here to be n minus 2, this is like the simplest case that's not just identity, not just a block of 1s. This corresponds to the hypercube problem. So basically the question is, if I have n bit strings, and I'm checking, I put a plus if the difference in the Hamming weight is exactly 1 or less than, or if they're equal, and I put minus if the Hamming distance is at least 2. This was conjectured in a previous paper of Puya, Hamid, and the other people who I don't remember their names. Diana? Oh, okay. That this hypercube must have super constant sign rank. But we don't know that, right? But then you might say, well, that might be too hard. What if you just try to make the threshold be smaller? What if the threshold maybe, I don't know, it's something else? Again, minus square root n or n minus some constant like log n or something.
It was bent.
Okay, sorry about that.
Wrong thing.
I mean, to be fair, it wasn't here, so but the issue is that in this one, then the gamma to infinity is not bounded anymore, right? So you really want the separation to be for these bounded gamma to infinity. Okay, so no more questions? I mean, yeah, okay. So now switching to a different pair of parameters, another natural one to look at is the connection between approximate gamma 2 and gamma 2. So again, Lindenstrauss showed that this approximate gamma 2 norm is highly relevant because it provides a really strong lower bound for this public bounded error randomness. And because of this, it's extremely important in communication complexity. And gamma 2 norm also corresponds, if you lower bound on, prove lower bounds on gamma 2, that gives you good lower bounds on some other models of communication that are important that I won't describe here. So these are crucial in communication complexity. Also, yeah, this notion of gamma 2 norm is a type of factorization norm that's well known in Banach space theory, apparently, and initially it was introduced by Lindenstrauss in communication complexity, and they brought it in and have used it to prove lower bounds. And so this question was phrased in this Lindenstrauss and also in this recent work of Pitowski, Morgan, and Adi Schreiben, that can one substitute this in this lower bound, can one substitute actually this approximate by just the exact gamma 2 norm? This would provide a widely powerful method for public randomness. Okay. But so what we showed was that with Ben and Morgan and Hamid, we showed that this is not possible. So we showed that there is a matrix whose public randomness communication is logarithmic in the maximum possible. So log n is, you can always achieve that, it's the log of that, but this gamma 2 norm is poly n. So if you don't care about communication complexity, I'm just saying I'm providing a strong separation between approximate gamma 2 norm and gamma 2 norm. So we give a matrix whose approximate gamma 2 norm is only polylog. Whoa. So this is capital N. Okay, so it's polylog n, but it's gamma 2 is poly n. Okay, so I'll also just tell you what the construction is. The construction is again another variant of inner product. Turns out everything is inner product with some twist. So here the inner product function that we're working with is the following. Again, I look at these integer points between minus n and n. Previously, in the previous construction, the original construction in the other question was I put a plus if the sign is positive, right? But we proved that it's extremely hard for randomized communication. Like gamma to infinity was almost maximal, right? So if you want to use a randomized protocol to solve that, you really need linear in n. So like you can't beat the trivial bound. But here it turns out that you can just check equality. So I just want to say if this inner product is either 0 or non-zero. So why is this so easy? Why does it have some? I can easily check if this is true, if it's 0 or non-zero. Well, if you don't know communication quality, I mean, it doesn't make sense, but you can do mod, pick a random prime and look at mod of that and exchange that number. And if it's 0, it's going to be 0 with high probability here. And if not, it's not, right? Okay, so this was for 3-dimensional vectors. A natural thing to ask is, what can you reduce the dimension by 1? What about 2-dimensional? Like if this was a 2-dimensional question. There, it's trivial. Basically, it boils down again to the identity function. So 2-dimensional inner product is the same as identity of a bigger matrix. Because you can say, you just want to check this condition. I'll just put the same as this and divide. So you have, this is now just checking if this is equal to that. So that just corresponds to an identity matrix where the rows correspond to these things, right? So their approximate gamma 2 norm is constant, but the gamma 2 norm itself is only polylog n, so you can't say anything about that. Okay. So I'll now just describe some open problems if there are no questions about. Oh, actually, maybe one interesting thing that people here might appreciate is that how do we prove that this is hard? We want to give a strong lower bound on the gamma 2 norm of this. Basically, the reason that this is hard is because it contains, as a submatrix, this tight example for Zemeridi-Trotter. So what's the tight example for Zemeridi-Trotter? You have this arrangement of this skewed grid, and then you look at the lines and look at the incidences, right? Where the lines don't have an extremely high slope. Yeah, basically we show that the gamma 2 norm of this submatrix is large. So it requires a lot of work because if one makes everything mod p, it's easy to prove lower bounds on the gamma 2 norm, but on the other hand, its approximate gamma 2 norm will also be big. So you can use the spectral bounds to get that, but in the n integers, it's more work. But yeah, I want to describe more about the detail of the program. Okay, so now let's just discuss some open problems. There are many of these pair relations left, so let's see which ones are interesting. So still, the question that the separation we got was polylog n versus poly n for approximate gamma 2 or a gamma 2 infinity. So can one get a constant versus poly n? Okay, so possibly this is doable, but I mean, I'm not sure if it's true, but we only get a, yeah. So Lineal-Schreiber showed that it's cannot be too ridiculous, the separation. To say if this is constant, you can't this cannot be larger than square root n, but this doesn't refute the possibility of some poly n, some other exponent. Okay. So another question that we already discussed is for total matrices, can you obtain a separation between this gamma 2 infinity and sign rank? And here, all I'm asking is that some matrix with constant gamma 2 norm, but super constant sign rank.
First problem, what's the best one? It's
So what I discussed was like polylog versus poly n.
best one for constant.
For constant, okay, yeah, constant would be just 1 versus polylog, right? So this question is also interesting. If I make the gamma 2 norm itself bounded, with the exact gamma 2 norm bounded, does it imply that the sign rank must be bounded? So why is this interesting? Because in this paper, Hamid, and which is the paper that I mixed with the other one, is that they show that this follows for Cayley graphs of a boolean group. This follows from this quantitative strong bounds for Cohen's idempotent theorem. That's due to brilliant standard. So basically, they
it also follows for non-abelian groups for any finite.
Why did I write? Right. Any. Okay. So we have good bounds on non-abelian setting as well. But so for all Cayley graphs, this is true. Exact gamma 2 norm gives an upper bound on sign rank. But is it true for arbitrary matrices? I mean, the hope is like maybe you can, if I give you this extra condition, you might do something wildly smarter than Johnsson-Lindenstrauss in some sense. And another relevant question that's not about the pair of relations is about another type of structure. You want to say, pick any of these parameters. If it's constant, can you find a big monochromatic subrectangle? So this turns out to be an extremely important problem for any choice of these parameters. And the one that's, I mean, the weakest assumption is if I just say gamma 2 infinity is constant, which corresponds again to this randomized public bounded verticals. Can I find a dense monochromatic subrectangle? By a rectangle, I just mean a submatrix. So it's like a subset of the rows times the subset of the columns where everything is either plus or all minus. I'm not sure who initially asked this question. So I thought maybe in a paper of Pitasi and Mika and I think the P versus NP question, P to the NP is asked there, but maybe yeah. But anyways, so
yeah.
But well, another related question is if I just make sign rank to be bounded, can I find a big monochromatic rectangle? And this is a result of Alon, Park, Pinchasi, Duri, Chik, Sharir, and also Fox, Park, Shuk, who give it, who show that there's always a monochromatic rectangle of density, at least this 2 to the minus sign rank.
That's false, then it at least settles the relation. Sign rank.
What is false?
Problem 4 is that it separates.
Mm-hmm. Right. Yes. Yeah, the answer to this was false, then would also imply that there is a matrix whose sign rank is constant. Yeah, whatever. Just something around said that I don't know what. Okay, so these, yeah, I think that's it.
Do you expect all of these to be true?
Well, I mean, this one is natural. It's true for Cayley-Glass. Why not for all matrices? The total one, I think it should be true even just for this hypercube construction. I'm thinking about it a lot. But, and this one, yeah, this one is also interesting. I mean, people believe it usually. Like, so you say,
I don't believe.
You don't believe it? Okay.
That's just like lack of examples.
Oh yeah, that's a very good point. Yeah, exactly. So the issue is in the entire field as literally we don't know any other than this identity matrix and this hypercube. Right? So that's the only 2 examples we know that has bounded gamma to infinity. No? Or maybe instead of like the threshold, Hamilton 1 was Hamilton 2 or some constant. Same example. But other than these 2, we just don't have any examples to work with. So that would be interesting to find some widely new matrices that have bounded gamma to infinity norms. Yes.
So I couldn't help noticing that, tell me if this makes sense, that like in your partial matrices that you use to like witness large values parameters, they're a lot like Salil's graphs, right? The sort of geometry, I mean, the sort of issue is the same. You're sort of picking points on SD minus one and sort of keeping track of like whether like the entries that are specified in your matrix, I think are basically the adjacency matrix of your geometric graph. And I guess I mean, since it's kind of my job to like write a thing where I like summarize all the stuff that happened in the conference and put it together, like is there some reason that these same kind of objects come up for both of these?
So I mean, again, I feel the difference with these geometric graphs is there you embed the graph. So you embed vertices, which means you have only one map. It's not a bipartite concept, right? So you can't, if I tell you embed this independent set in a low dimensional space, you just can't do it, right? Because that means every pair point has to have inner product at most 0, right?
Yeah.
But if I have the matrix here, all block of -1, it has constant sign rank. I just embed it in one dimension because I can choose a map here and a map here. I just assign all of these here to positive +1, assign everybody here to -1, and everybody always has an inner product -1, right? So it's a wildly different concept. So yeah, the complete bipartite graph cannot be embedded in any dimension. I mean, you need dimension full. In fact, it's an interesting concept that I recently learned about from Brennan, that the geometric, yeah, basically you're given a graph. What's the smallest dimension where you can embed it, where you look at it as a geometric graph? So it's this intersection of some spheres, and the spheres can be arbitrary. So everybody has the same radius, but you're allowed to change the radius of the sphere. And there, it's known that complete bipartite graph, some packing argument, you need essentially the best, this number of the vertices, basically. But here is just triple, so it's not rank 1. It's a much different concept.
Any more questions? Okay, if not, let's thank Kaave again.